Hi, we are Group 1 in Section 1 of the Fall 2017 Senior Lab. The group members are Robert Ernst, John Mantese, and Emma Willett. For our video article, the experiment we completed was caffeine extraction. The objective of this experiment is to observe how manipulating specified variables affects the amount of extracted caffeine from coffee grounds over time. The United States is the #1 coffee-consuming country in the world. Approximately 3 in every 5 people drink coffee every day, and coffee represents 75% of all caffeine consumed. The motivation for this experiment is to determine optimal conditions for the extraction of caffeine from coffee grinds. These conditions include, but are not limited to, the optimal temperature, the optimal grind size, and the optimal flow rate.
In this lab, chemical extraction is used to separate caffeine from the coffee grounds. In theory, caffeine is more soluble in dichloromethane than it is in water. Coffee grounds contained in tea bags are placed in deionized water so that caffeine is allowed to leach into the aqueous phase from the solids. When the aqueous phase is combined with dichloromethane in the separatory funnel, caffeine is expected to pass into the organic phase because of the solubility preference of caffeine. The amount of caffeine in dichloromethane is determined by measuring the absorbance of light passed through a quartz cuvette. Absorbance is read by a spectrophotometer and converted to concentration using a calibration curve based on data from previous experiments.
To start, tea bags are opened and the tea is removed. Coffee grinds of the desired grind size are then massed out to 3 grams and placed inside the empty tea bag. The tea bag is sealed and is now ready to be used for the experiment.
The next step involves heating DI water on a hot plate to a desired temperature. After the desired temperature is reached, the pump is turned on and the flow rate is set. The valve for the collection chamber is kept closed until the desired volume of 100 milliliters is reached. After the desired volume is reached, the valve is carefully opened and the outlet stream is set to about equal to the flow rate of the pump so that the volume stays constant within the collection chamber. After the volume is seen to stay constant, the tea bag is placed into the warm water and a timer begins. After 3 minutes have passed, 3 samples are collected in 15 milliliter increments. The tea bag is then removed and the setup is restored and ready for the next trial. The next step involves taking the 3 samples over to the fume hood. First thing to note is that the individual working under the fume hood must be properly equipped with silver shield gloves and a full face mask due to the work required with dichloromethane. Under the fume hood, dichloromethane, or DCM, is very carefully handled in the following steps. First, the 15 milliliter sample is transferred into the flask. 15 milliliters of DCM is then measured out in a graduated cylinder and poured in the same flask with the sample. The flask is then sealed with the cap and removed from the ring stand. While keeping pressure on the cap, the flask is then inverted 3 times, making sure not to shake the flask, but rather just allow the phases to pass each other. Also note that after the second inversion, the valve is opened to release the pressure buildup in the flask. After the final inversion, the flask is then placed back onto the ring stand and the bottom phase is collected in a beaker below. This procedure is then repeated 2 more times using the remaining coffee extract in an attempt to extract any residual caffeine that may still remain. Lastly, the collected caffeine extract and DCM is then transferred into a cuvette. This cuvette is brought over to the spectrophotometer. The sides are wiped down with a Kimtech wipe, and the cuvette is placed into the slot within the spectrophotometer in a way where the clear sides are facing the front and back of the machine. The absorbency can then be seen on the digital display.
Chemical waste is then disposed of into properly labeled containers. The aqueous phase containing coffee waste and trace amounts of DCM is poured into a secondary transfer container after each separation is completed. When all trials have been completed, this container is emptied into a larger amber container with the proper hazardous waste tag. Organic DCM waste is transferred to a separate secondary container and then to a larger waste container when the secondary container has filled. Acetone waste used to clean lab equipment is deposited into its own labeled container.
The parameters we varied were the temperature of the heated DI water, the grind size of the coffee grinds, and the flow rate of the pump and outlet stream. The independent variable in this case would be either temperature, grind size, or flow rate, while the absorbance measured is the dependent variable. The temperatures used were 65, 70, and 75 degrees Celsius. The grind sizes used were fine, and medium coarse. Lastly, the flow rates used were readings of 10, 15, and 20, which corresponds to 1.11, 1.71, and 2.26 milliliters per second, respectively.
To determine concentration from the absorbance value that was recorded, we used a calibration curve. This was a simple calculation and only required the equation for the linear line given from the slope of the calibration curve. To determine the corresponding real-world flow rate from the arbitrary reading given on the pump, a flow rate calibration was run. For this, we collected water over a specified time interval in a beaker. After massing the beaker before and after, we could determine the actual flow rate in milliliters per second. From the data collected when varying temperature, we can see a general trend that is consistent with our hypothesis. Our original prediction was that as the temperature increased, the concentration of caffeine extracted from the coffee grinds would also increase, because an increase in temperature would lead to a higher diffusion rate of caffeine into the surrounding hot water, as well as higher solubility of the coffee grinds.
When varying grind size, the data shows no consistent trend. The medium coarse performed the best at extracting caffeine, while the medium fine performed the worst. The initial prediction was that as the grind size increases, the concentration of caffeine would decrease because the surface to volume ratio would decrease as the grind size increases. The data does not show this and instead shows no general trend when relating concentration of caffeine extracted to grind size. Lastly, when varying flow rate, the data seems to show consistency. We initially predicted that as the flow rate increased, the concentration of caffeine extracted would decrease. This is because as the flow rate increases, the residence time decreases, and the caffeine extracted would, as a result, decrease. The data shows this trend. As we increase the flow rate, the concentration of caffeine extracted from the coffee grinds decreases.
Possible error may have existed within this experiment. In regards to varying the grind size, the method of which this was accomplished was through the use of a coffee grinder. The coffee grinder may have not produced reliable grind sizes, and this may have affected the absorbance collected for those trials where we altered grind size.
That temperature's kind of high. No, I'm not going to add this. Actually, I am going to add this.